Thanks, Marissa. So I'll be presenting on a preliminary validation of CSHORE-Veg. So just introduction to our motivation behind simulating hydro and morphodynamics through vegetation. So various experiments and in situ observations show that salt marshes can attenuate waves, reduce surge, and stabilize shoreline and wetland. They are, according to satellite imagery, decreasing at a rate of about 0.28% per year globally, but that also means that implementation and restoration of salt marshes is expected to increase. So we would like to know, we know that salt marshes can be used as a natural or nature-based feature for flood risk management, but their capabilities change over time. So we want to know how well do these NMBFs perform in the face of high wave height events and surges during storms. Currently, we have continuous monitoring of coastal wetlands, but it's pretty lacking, and it's difficult to understand long-term interaction between the hydrodynamic processes and the ecosystem. So we want to know if we can use a predictive simulation model to quantify the capacity and benefits of salt marshes for flood reduction, erosion protection, and beneficial use of materials. Our objective is to validate and test the sensitivity of the CSHORE-Veg model to provide an accurate simulation result of wave attenuation and wave setup by taking into account differences in biomechanical features of different vegetation, such as their flexibility, bending, and breaking. So we'll look at the development of CSHORE-Veg and some of its capabilities and how it approaches these. So the first is to provide accurate hydrodynamic results about wave attenuation and setup. The way it approaches this is by we've implemented new formulations to better predict wave damping and vegetation resistance forcing by considering the nonlinearity of waves through shallow water. The next capability is to provide a model for taking into account biomechanical features of various plants. We've developed a general algorithm to predict wave energy dissipation and momentum reduction due to flexible and rigid vegetation. And another capability is providing a predictive formula for calculating the vegetation drag coefficient so that the model can be used for the prediction simulations of different types of plants. And so we use field data from a salt marsh to develop and validate a general CD formula. A future capability we'd like to integrate with morphological models within CSHORE to provide accurate results on sediment transport through vegetation. So the phase averaged wave energy equation in the cross-shore direction is the governing equation for the wave model in CSHORE. Here, E is a specific wave energy, omega is the intrinsic angular frequency, Qx is the cross-shore volume flux, dB is energy loss due to wave breaking, and dF is the energy loss due to bottom friction. This equation was modified in CSHORE-Veg then to include energy dissipation due to vegetation resistance. And there's two models that are included as options to determine this energy dissipation. The first option was proposed by Mendez and Losada in 2004, and this extended the formula in Dalrymple et al. 1984 to random waves. So dV is the expected value of time averaged energy dissipation rate due to vegetation. BV is the plant area per unit height of each vegetation stand normal to horizontal velocity. NV is the number of vegetation stands per unit horizontal area, and we call that population density later. CD is the depth averaged drag coefficient. Omega and K here are the representative wave frequency and wave number. So Mendez and Losada used the peak frequency and corresponding wave number as the representative values. It's valid for narrow-banded wave spectra. In the second model, Chen and Zhao 2012 used a more general theoretical model for dV. this model requires more information about the wave spectrum to perform the integration over wave frequency. And for the following validation, we've chosen to use the Mendes and Losada formulation with the more basic information of the wave properties. So this is a phase and depth average momentum equation in the cross-shore direction, and it's what CSHORE uses as the governing equation for its flow model. Here, SXX is the cross-shore radiation stress, tau BX is the phase average bottom shear stress, tau SX is the phase average wind-induced shear stress, and FV was included by CSHORE-Veg to include the drag force on the water column by vegetation. So you see here that what's included in this, we've only chosen a weak mean current, and so there is no effects of return flow within the vegetation, but we're considering the drag force on the water column by vegetation waves. And there are two models that CSHORE-Veg uses to handle that calculation. And we can also include the drag force on a water column by vegetation in current waves. So FVCW accounts for the mean current as produced by the Stokes drift. So the first model is the parametric model developed by Zhu and Chen in 2019. This uses the stream function wave theory, and we chose this to validate since it accounts for both submerged and emergent vegetation cases, as well as wave nonlinearity using F alpha, a correction factor. So this was included in a database of 6,066 wave conditions, and FVW was calculated according to a stream function wave theory in varied heights, periods, and depths, then used to calibrate F alpha for each scenario. So as you run the model, it will look up F alpha and apply it based on your input wave conditions. The second model is a hybrid model, which uses both the stream function wave theory for submerged vegetation, then linear wave theory for emergent. And this has been tested a lot and typically agreed that for emergent vegetation, linear wave theory holds. So why do we need nonlinear wave theory incorporated? Here's a definition sketch of wave vegetation interaction and represented by cylindrical elements and the resulting wave average net forces and shear stress acting on the water column, and this effect on the wave setup or mean water level. So in the top picture A, we see the presence of rigid elements, and the results in the radiation stress gradients in relatively deep water, resulting in a reduced wave force and mean vegetation force due to the mean flow or undertow. So B in the bottom shows this in combination with submerged cases. C in the middle shows emergent cases, and D shows nonlinear waves in combination with submerged vegetation. And we can see that in C and D, there are cases when the phase and depth average drag force due to vegetation is non-zero. So linear wave theory is underestimating the vegetation resistance against waves. Finally, these are a few of the options for an empirically derived CD formula included in CSHORE-Veg. Empirically derived formulas are pretty common practice for experiments. There are virtually these best fit curves for every experiment, and typically they're fit to the Reynolds number, which is the measure of inertial to viscous forces and defines flow regimes from laminar at low numbers to turbulent flow at higher numbers. Usually a best fit curve to the equation is fit to the highlighted equation that's suggested in Kobayashi et al. In 1993. All other terms in the momentum equation, or it's calibrated by all other terms in the momentum equation calculated with measurements, or wave action equation, calculated with measurements, then the vegetation and energy dissipation term is considered the last term, and the drag coefficient is calculated from there. In the case of Zhu et al., the calibrated drag coefficient was started at 1 and iterated or increased incrementally until the vegetation dissipation term fit to 2% of the calculated value. This is the structure of the vegetation model in CSHORE-Veg. So the inputs for the flexible model or flexible vegetation are biomechanical properties. So VV is the vegetation width, HV is vegetation height, E is the Young's modulus, and NV is the population density. For rigid vegetation, it only includes the width, height, and population density. Next, you can choose which drag coefficient formulation you'd prefer and how you'd like the model to calculate energy dissipation due to vegetation resistance and the phase average depth integrated drag due to vegetation. And after CSHORE is run, you have a record of the calculated drag coefficient, effective plant height, and the original height of the stem. So what is effective plant height? This is calculated using a scaling law for a seagrass meadow proposed by Lay and Neff in 2019. So the scaling law was developed assuming uniform wave properties throughout the water column, so linear wave theory and fully submerged vegetation. Here, LEM is the effective stem height, CAW is the wave Cauchy number, L is the ratio of flexible stem length to wave excursion or orbital radius, LB is the flexible stem length, and LR is the rigid stem length. So the wave Cauchy number is the ratio of hydrodynamic drag to the restoring force due to blade stiffness. Previously in CSHORE, any effects due to vegetation would have been estimated and included in the bottom friction factor. So this method using the scaling law incorporates the biomechanical properties of individual vegetation and gives us a more inclusive representation of how different species of vegetation are influencing local hydrodynamics. So this is just highlighting how the effective plant height is incorporated into our model. CSHORE-Veg utilizes effective plant height as determined by the scaling law as our plant height in both the wave energy dissipation and drag force calculations for the wave action and momentum equations, respectively. Again, we need a drag coefficient formulation ready for quick estimates so that we don't have to calibrate and empirically derive a formula every time the model is run. And so we did this using a salt marsh experiment. So this is a closer look at the unified drag coefficient formulation as proposed by Zhu et al. In 2023. First, the scaling law was calibrated, or the drag coefficient was calibrated using the scaling law and the wave action equation for observations at each wave gauge. And next, this was plotted against the Reynolds number and fit to a curve that gave the unified formulation on the right. It is considered unified because it should be applicable to both flexible and rigid vegetation and also used in both the energy dissipation and drag force calculations. It is assumed to work for the drag force as well because the differences should be small. And it's been validated with for experiments in Zhu et al. 2023. And we'll take a look at the sensitivities to some of the parameters in a few experiments. The first experiments from Anderson and Smith in 2014. This is performed in the UC's wave flume, and the setup shown below. So the depth varied from 12 inches to 21 inches. Vegetation height was 41.5 centimeters. Young's modulus of vegetation was given at 172.4 megapascals, and the population density ranged from 0 to 100 and 400 stems per meter squared. The vegetation was physically modeled with a cross-linked polyolefin tubing, and the meadow was 9.8 meters long. The simulation results were compared with the observations from wave gauge 5 to wave gauge 13. The models we've chosen for our simulation are the unified formulation for the drag coefficient, Mendes and Losada formulation for the vegetation energy dissipation, and the parametric model for the vegetation drag resistance. So first I decided to test the sensitivity to the Young's modulus. So the Young's modulus is a measure of stiffness or compressibility of a material calculated by the slope of the linear elastic region of the stress strain curve of the material. So cross-linked polyolefin tubing, XLPO, doesn't have a Young's modulus because it doesn't have that linear elastic region. So a different method of calculating the slope was used, 2% secant modulus, which typically underestimates the Young's modulus in materials that do have a linear elastic region. The material was chosen to represent Spartina alterniflora, a common seagrass at field sites in Louisiana where there's ongoing campaigns. And in some studies, 172.4 megapascals represents this seagrass fairly well, but in other studies, they found this varies by an order of magnitude. So I decided to vary the Young's modulus by plus or minus 50% to see how sensitive our simulation was to this parameter. So I simulated wave height attenuation using CSHORE-Veg to determine how this parameter varied. Using the original value of 172.4 megapascals, our simulation does really well with an R-squared value of 0.99 and a normalized root mean square deviation of 0.035. And when we vary the Young's modulus by 50%, we don't really see an appreciable change in those values. So this indicates that we can have a pretty wide uncertainty of our Young's modulus, and the simulation can still produce an accurate prediction of wave height attenuation. Next, I wanted to investigate the sensitivity of a model to submergence of vegetation. So the Anderson and Smith cases have some emergent vegetation, either due to the initial still water level or the size of the waves. So their findings suggested that stem density becomes more influential in wave decay with greater emergence. So K on the y-axis is the wave attenuation coefficient quantified by an exponential decay function. And on the x-axis, LS over H is the plant height over the water depth, where a value greater than 1 indicates emergent vegetation. The square points here are the control case with no vegetation. The circles are 200 stems per meter squared, and the triangles are 400 stems per meter squared. So as expected, the highest population density at 400 stems per meter squared has the highest wave attenuation. And as vegetation becomes more emergent, we can see a greater difference or spread between those cases according to population density. So first here are the simulation results with a water depth of 18 inches. So we have the greatest spread of incident wave cases here and a really good performance with an R-squared value of 0.99 and normalized root mean square deviation of 0.03. So with higher waves, we do get some vegetation emergence. And on the left, we're cycling through normalized root mean square wave heights with the simulated represented by the solid lines and observed measurements in points. So our high population density is in red, medium, 200 stems per meter squared is in black, and no vegetation in blue. We can see for the cases with a greater wave height as we're cycling through from 8 to 10 centimeters, where the vegetation is slightly emergent, the simulation underpredicts the wave attenuation in those vegetated cases. And then for smaller wave heights where the vegetation remains submerged, there is a slight overprediction of wave attenuation. So although our model still performs well, those slight deviations can be noted. So here are some fully submerged cases at a depth of 21 inches, and we're still getting fairly good model performance, just a lower R-squared value because the incident wave heights are very close together, and so it's really sensitive to any deviation in the values. But our normalized root mean square deviation is even smaller than in the 18-inch cases, so we're still getting pretty accurate predictions of wave height attenuation. Here are the fully emergent cases where the water depth is at 12 inches, so below the vegetation height. We're still getting good model performance, but if we just look at the very small incident wave cases, we can see some divergence from a one-to-one simulation to observation value. So our simulation here is over-predicting the wave heights. And one hypothesis for those cases that we can understand from our unified drag coefficient to Reynolds number curve is that we have exponential changes in values at lower Reynolds numbers where the wave height is also low. So we would like to validate using experiments that have lower Reynolds numbers. And these lower Reynolds numbers are also more common where emergent vegetation grows rapidly since it's a gentler environment and doesn't stress the vegetation caused breaking. So it is an important part to understand the hydrodynamics in many different in-field vegetation cases. The next experiment was from Jodoff 2015. It was done in Terrebonne Bay, Louisiana, during Tropical Storm Lee. So this is an in situ experiment. It was measured over 2 days, and the root mean square wave heights ranged from 43 to 83 centimeters, peak period from 2 to 4.5 seconds, and still water level from 0.5 to 1 meter during the storm. The site survey also found the biomechanical parameters of the plants. So the stems, Young's modulus was 80 megapascals. Stem population density is 400 to 420 stems per meter squared and spatially variable across the cross-section. The blades, Young's modulus was 50 megapascals, and there was an estimated 5 blades per stem. So the population density was 2,000 to 2,100 blades per meter squared. And the effective plant height calculated ranged from 0.21 to 0.23 meters. Again, we're using the same formulation options that were chosen in the simulation. So the unified formulation for the drag coefficient, Mendes and Losada for vegetation energy dissipation, and parametric model for drag resistance. Here are the results from the simulation. So the blue indicates earlier measurements and the yellow are later. So we can see that the storm occurred during September 3rd and from the increased wave heights and still water level that we included in the simulation. And we're seeing less agreement with those greater wave heights. So we may be able to increase accuracy using more information about the wave spectra and incorporating this into the calculation of energy dissipation because there were some bimodal waves present, but we're currently just using representative wave properties such as the peak period and wave height. So another way to increase accuracy could be including the bathymetry changes with time. So currently the simulation doesn't include an updated bathymetry. Our R-squared value is 0.86, which still indicates that we're getting fairly good simulation performance given the uncertainties in the measurements. The last experiment was another wave flume experiment done by Ozeran in 2011, and this experiment gives us some preliminary results of model performance on wave setup. So this vegetation was modeled with wooden dowels, so very rigid vegetation with a height of 0.2 meters, a width of 3.175 millimeters, population density much greater than the other cases with 3,115 stems per meter squared, and the Young's modulus of 10 gigapascals, which is really large. So our scaling law effectively treats the effective plant height as the original height. And we're using the same formulas for the drag coefficient, energy dissipation, and drag resistance. So here are the experiment and model parameters. As case number increases, so does the significant wave height, energy flux, and nonlinearity of the waves. Significant wave height varies from 3.5 to 8 centimeters. Peak period varies from 1.2 to 2.4 seconds. So using our unified drag coefficient formulation, we see a decrease starting from 10.25 to 3.5, and that's expected because the lower wave heights correspond with lower calculated velocities and lower Reynolds numbers at case number 1. And so as that wave energy increases, then we should get higher Reynolds numbers and therefore a lower drag coefficient. The bulk calibrated drag coefficient was actually estimated for this experiment at about 1.7, according to the observations. So our unified formula is off by about an order of magnitude in some cases. We also used another calibrated drag coefficient that gives us closer values to that bulk calibrated value. So that was calibrated by Yan, and that will be used to compare our results from the unified drag coefficient. So clearly with the unified drag coefficient calculations, we're getting a really overestimated wave height attenuation. So the drag coefficient calculated with the unified formulation is very high in the lower Reynolds number regimes. And in these plots, the non-vegetated cases are shown in red and the vegetated cases are shown in black. The vegetation is included in the green vertical lines. And we see that shoaling may actually be more dominant in this case, which makes sense because the vegetation was present on the slope here. And these drag coefficients vary exponentially. So we, again, know that we're present in the lower Reynolds number regime. So these are the results using Yan's calibrated drag coefficients, and we get a much better agreement with these results. So there's an indication that we need to change that unified drag coefficient. So these are the calculated ones for the Azurin experiment cases, shown in red, and the solid black line is that CD to Reynolds number curve as using the scaling law. This isn't rated for any Reynolds numbers lower than 312, but this maybe indicates that an even larger range from 600 should be used as a different regime for the Reynolds number to drag coefficient curve. Then looking at setup, here again, we get a really big overestimation of the wave setup by the simulation with higher energy. In the first cases, there seems to be a slightly better fit with the observed results. And this is just due to the mean current being very small. So generally, the drag coefficient is not dominant and the dissipation in general is smaller. We can see at the beginning of the canopy that there's an unphysical response right at the canopy edge. And that's due to a sudden jump in radiation stress that increases as the wave energy increases. So this could be happening due to a greater influence of the return flow in these higher energy wave breaking cases. So if we remember from the momentum equation in our calculation for the drag force due to vegetation, we aren't accounting for the return flow, which might help to balance the sudden increase in radiation stress. And here are the results using Ian's calibrated drag coefficient. And ultimately, these observations are probably too noisy to completely conclude model performance, but we can still see that overestimation happening as the case number increases and the wave energy increases. So we can see qualitatively, though, that wave setup can be reduced through vegetation, which is shown in our observations and also reproduced by our model. There is that overprediction, though, of wave setup as wave energy and asymmetry increase, which could points to needing to include the effects of return flow. Ultimately, we need more experiments, though, and especially field tests to quantify this. So CSHORE-Veg is a one-dimensional phased average model that includes many assumptions to simplify our governing equations in order to increase computational efficiency. And these assumptions are being verified to make this model as accurate as possible while still being quick to run. In the future, we'd like to increase the model accuracy to validate with more field experiments, especially experiments with lower incident waves and low Reynolds number and rigid vegetation. Eventually, we'd like to integrate sediment transport. First, we'd like to validate with the hydrodynamics first, and we might need to look into fluid scaling for this because some of the changes in these cases may be too small for the model. Finally, a sensitivity analysis may be done just to automate and find some of the parameters that are sensitive to varying wave properties. And we will also like to develop that regime-specific drag coefficient formulation, especially in the lower Reynolds numbers, and include return flow effects on the drag force. Finally, this is our open source GUI tool that was created to run CSHORE-Veg and visualize hydrodynamic predictions in vegetation. And this is provided in a Jupyter notebook, which calls the CSHORE-Veg executable program written in Fortran. So you can input your biomechanical parameters, wave properties, and bathymetry for this simulation. Here's a quick demo. So you can choose your project directory, which includes your CSV files of both bathymetry and your wave conditions. And you can input your vegetation parameters, so the stem width and population density and stem height, and morphological changes, and generate an input file that you can then use to run this executable file or executable program. And it only takes a couple seconds for many different wave cases. And then you can also plot your results in the GUI. And also save your results in a CSV file. So the saved parameters are the root mean square wave height and mean water level, drag coefficient, and effective plant height. Thanks. If you have any questions, this is our contact information.